Let's start with chip manufacturing. Chips or integrated circuits are the foundation of all electronic devices, from our smartphones to high-powered supercomputers. It was eye-opening to learn just how complex and precise this process is. Each chip contains billions of microscopic transistors, which essentially control the flow of electricity to perform computations. The process starts with a raw material called silicon, which is abundant in sand. It's quite fascinating to think that such a common material is the basis of technology that powers our world. The silicon goes through a purification process to reach a very high degree of purity. Then, it's shaped into wafers, which are thin, circular slices of silicon. This wafer serves as the base on which all the intricate circuits will be built. After that, the manufacturing process involves several detailed steps, including layering, doping, etching, and ion implantation. Each step is carefully controlled to create specific structures and pathways on the silicon. This is where science and art intersects because even the slightest error can render the chip ineffective. To put this into perspective, think of a chip as a city with millions of streets and intersections. Each street is a pathway for electricity, and each intersection represents a transistor. Building a city like this on such a small scale requires high precision, advanced tools, and an environment cleaner than any operating room. Even the tiniest dust particle can ruin an entire batch of chips, causing delays and financial loss. Watching the video on chip manufacturing, I realized how important each step is to ensure a working final project, and this complexity is a big reason why making chips is difficult, which brings me to the next point. The second video dives deeper into why chip manufacturing is such a complex and challenging task. As we demand more from our technology, faster processing speeds, higher efficiency, and smaller devices, manufacturers are tasked with creating even smaller transistors. Today's chips use transistors that are only a few nanometers wide. For comparison, a nanometer is about 100,000 times thinner than a human hair. When working at such a small scale, manufacturers face several limitations. First, there's the issue of heat. As you pack more transistors onto a chip, they generate more heat, which can damage the chip if not properly managed. Cooling is essential, but it's challenging to integrate effective cooling solutions on such a small scale. Second, there's the problem of energy efficiency. Transistors act like tiny switches, turning on and off to process information. But as we make these switches smaller, controlling them becomes harder. Electrons can leak from one part of a transistor to another, leading to inefficiencies. This phenomenon, known as a quantum tunneling, shows us that the law of physics start to interfere at extremely small scales. Lastly, there's the sheer cost. The machine used to make chips, especially those involving photolithography, can cost hundreds of millions of dollars. And because of the high precision required, only a handful of companies in the world have the capability to produce advanced chips. This explains why chip manufacturing is concentrated among a few large players. This brings us to photolithography, one of the most essential and fascinating techniques in chip production. Photolithography is a process that uses light to transfer a pattern onto a silicon wafer. This is done by shining light through a mask, which is like a stencil, to create the patterns of circuit on the chip. In the video, I learned about an advanced form of this technique called extreme ultraviolet lithography, or EUV. EUV uses extremely short wavelengths of light, which allows manufacturers to create even smaller patterns on chips. This is crucial for producing high-performance chips like those found in the latest smartphones and computers. However, EUV technology is incredibly expensive and requires specialized equipment that few companies can afford. One fascinating aspect of photolithography is how it has driven the miniaturization of technology. Every time you hold a smartphone, you're essentially holding the result of decades of progress in photolithography. Each advance in these technologies allows for more powerful chips in smaller sizes, making our devices faster and more efficient. This part of the process made me appreciate just how intricate and exact chip production is. It's not just about making something small, it's about making something complex and reliable at an unbelievable tiny scale. Now, let's talk about how CPUs, or central processing units, are created. The CPU is known as the brain of the computer because it handles all the instruction a computer receives. The process of creating a CPU begins with a design phase, where engineers map out the architecture. Designing a CPU can take years because it's a careful balance of performance, efficiency, and power consumption. One interesting point about CPUs is how they're constantly evolving. The CPUs we have today are drastically more powerful than those from just a decade ago. Each new generation of CPU improves on the previous one, not only in speed but also in efficiency and size. This process of continuous improvement in CPUs is what allows for the advancement of the technologies, like artificial intelligence and data processing. Once the design is finalized, it moves to the manufacturing phase, which includes the wafer processing steps we talked about earlier. This involves building the transistor layer by layer on the silicon wafer. Then, the wafer is cut into individual chips, each containing a CPU. From there, each chip undergoes rigorous testing. If it passes, it gets packaged and is ready to be installed in a device. Finally, let's look at the future trends in computer engineering and the technologies to watch out for 2024. From the last video, it's clear that the field of computer engineering is evolving faster than ever. Some of the key trends include artificial intelligence, quantum computing, and edge computing. Artificial intelligence, or AI, is pushing the need for more specialized chips, like AI accelerators. These chips are designed to handle the unique requirement of AI algorithms, which require vast amount of data to be processed quickly. As AI becomes more integrated into various industries, we'll see more demand for these specialized chips. Quantum computing is another exciting area, though it is still in its early stages. Unlike traditional computers, which use bits to process data, quantum computers use quantum bits, or qubits, which, which can represent multiple states at once. This could lead to breakthroughs in fields like medicine and cryptography, but there are still significant challenges to overcome before quantum computers become mainstream. Edge computing. is another trend that has gained popularity. With the explosion of LOT devices, there's a need to process data closer to the source to reduce latency and enhance security. This involves distributing computing resources at the edge of the network, closer to where data is being collected. Edge computing could revolutionize sectors like healthcare, automotive, and manufacturing. Reflecting on this topic has given me a deep appreciation for the complexity and innovation behind the technology we use daily. From the intricate process of chip manufacturing to the ongoing challenges of miniaturization, it's clear that each step in this process is crucial. The impact of the advancements in photolithography, the creation of CPUs, and the future trends in technology demonstrate how computer engineering is driving us toward a more connected and intelligent future.